Okay, let's start. Do you have any questions about the last lectures? Mm. Okay, so let's start. Today I want to talk more about conformal blocks, namely to give some more abstract definition of them. So the topic is a space or spaces of conformal blocks. So last time we defined a conformal block as some function that depends on how many, on 6 variables, I think, no, 7 variables. It was the 4-point conformal block. It was a conformal block that depends on delta infinity, delta 1, delta intermediate, or some index p delta, or maybe better to put it at the end, delta t, delta 0, delta p, c, t, and it was such kind of matrix element, some vertex operator, or how did we call them? O, delta 1 of 1, resolution of identity, y prime, L minus y prime on the highest vector, O delta t of t, delta t. And it equals to some explicit series like t to some dimensions 1 plus over 2 delta p plus times t plus some other corrections. And this is called a conformal block. So it is some function, just one object. And its computation involved some notarial procedures when we had to move these VRSR generators through the vertex operator. We used some commutation relations, and finally it turned out that all these matrix elements can be computed and reduced to matrix elements for the highest vectors. And now I want to and put it in some more general context. So, last
time we computed the first factor, and there is no dependence on the central charge.
Of course, it appears in the next terms from this scalar product, because when we compute scalar products, it appears from the commutation relations. So we computed, for example, this matrix at the level 2, and it was already within central charge. And there is some funny story about isomorphism CFT correspondence that this formula was actually written in some Jimbo's paper, but it was written only with this terms. So people who studied this so recognized this expression that it is the first part of conformal work. But since this expression was not computed to higher orders, they had to compute it themselves and then solve the equation for central charge. It turned out that central charge equals to 1. It was precisely about this formula. I forgot precise signs in this brackets, but it is quite a recognizable structure. Like 3 out is here, 3 out is here. Okay, so more general phenomenon. So suppose that we want to define we want to define correlation functions in our theory. And these correlation functions should be defined for arbitrary fields, for arbitrary vectors in the Hilbert space. So what is the correlation function? It is some sphere or Riemann surface with some insertions. So something like this or something like this. So here we have some vectors, v1, v2, and so on. Also here. So we have correlators of the form, so we can denote it as the correlator of this form. So let us use maybe some points z1, z2. Let us use this vertex algebra notation, maybe vertex algebra or maybe such, no, let it be vertex algebras. And this correlator is computed on a sphere. And here the same can be computed on a torus or on some higher genus Riemann space. C mod 1 tau. So these correlators are functions from the tensor power of the Hilbert space. Where? Z1, V1. So it takes a point and a vector in the Hilbert space and puts the operator that corresponds to the state to point Z1. So if all these V's are highest vectors, then it will be the correlator of primary fields, but not necessarily. And they are defined for any external states. And so this correlator should satisfy uh, uh, so we can say that this z1, well, if we put here, if we leave here empty dot, well, zn, then it will be a function from h, example delta 1, tensor h and delta n, to numbers, since it takes n vectors in the Hilbert space, which I identified with some operators by the operator state correspondence and gives some number. So it is a representation of the Irregular algebra or of some other algebra if you work with some other algebra. So yes, so maybe we can put here also central charge. So there is some obvious property of this correlator that if we consider the integral of this kind, dw t of w, this will be the integral around around all these insertions. Epsilon of w, y of z1, is this obvious, because the picture is the following. We have the sphere, or not necessarily sphere, it can be some torus. And, we have this integral around all singularities. So this epsilon should be homomorphic inside the epsilon of w dw homomorphic in CP1 without all these points. So is it clear? But on the torus it is the same, because let me draw this torus in this way, and so we have some points here, for example 3 points. There are integrals around them, and if try to move this contours to its boundary, we get what on the contour of this form, and it equals to 0 because each boundary is counted twice. And it works the same for arbitrary Riemann surface, because in that case we will have this polygon, for example octagon, and it transforms to the integral over the boundary of this octagon, which is 0, because again each boundary is counted twice with the opposite signs. Hmm? Contractible. No, it's not about path, it's about class in homologies. So it's homological to 0. Or you can say that it is the only boundary, and we write sum of all boundaries. No, how to say it? Oh, but it's clear that such a contour is contractible, right? No, not contractible, but 0 in homology. And since this epsilon is holomorphic, then we don't find any singularities, and it is so all this is holomorphic. And here one important point is that this epsilon is not a function. It is a component of the vector field. Because T of W has dimension has dimension 2, so to get something that is one form, we should multiply dw, T of W, and something of dimension -1, namely epsilon. It's for the Virasor. For Kac-Moody. It should be again in the same integral. So here we have some currents with some Lie algebra index of W, psilon of W. Oh, and what can we say about epsilon here? What should it be? Hmm? Yes. because this is already of dimension 1, so it can be integrated with dw. And as it should be, it is a function because it is just some local transformation that does not touch coordinates. Mm. In this case, Varsoa representations should be replaced with Kac-Moody representations that contain inside one or usually more Varsoa representations. And since there is embedding of this algebras, then representations can be decomposed into representations of the algebra of the algebra which is the subalgebra of this Kac-Moody. Yeah, and so let us denote this relation by star, and maybe in this by 2 stars. So space of conformal blocks in space of linear functions. Functions or functionals, I don't know what is correct. On such tensor product. In the Virasora case, or for the Kac-Moody case, they will be labeled by k and lambda, the highest weight. So space of such linear functions that satisfy such conditions, star or 2 stars. So is the definition clear?
Now they are like correlation functions with endpoints.
Yes, a kind of all possible correlation functions that satisfy conformal word identities.
But before we define the conformal block for the 4 point, for operators.
Yes, and we also fixed the intermediate dimension. So we'll discuss it a little bit later, but for now, you can think that all such conformal blocks with all possible intermediate states and with all possible descendants inserted here, 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 and here. So, such space is in the space of conformal blocks, of 4-point conformal blocks. So these identities, for example, don't care about such Penn's decomposition of our Riemann surface. Hmm? All potential correlators. In a sense, they clearly form the linear space. So this linear space can easily be infinite dimensional. So and so it's kind of difference between the space of conformal blocks of physicists and for mathematicians. So for physicists, I think conformal block is a special function. For mathematicians, quite often conformal block is just some vector in this vector space, in the space of conformal blocks. And so both points of view can be useful, because this is, for example, one example of conformal block, but it might happen that the correct a correct element in this vector space is something different. For example, some infinite linear combination of such conformal blocks. So. Uh, yeah, so let us consider some examples of such spaces. We already know a lot about them without saying it explicitly. But for example, what is the space? What is the dimension? What is the dimension of such vector space? Let us consider how to draw it. Let us consider the two-punctured sphere. And here we have h delta 1, c delta 1, h, c delta 2. So if you try to apply this definition. Hmm? No. So there are functions. Let us write this definition. So let us say that these points are 0 and infinity. So we have y of infinity, v infinity, and y of 0, v 0, and there is the integral of T of W. What are the vector fields holomorphic on such sphere without zero and infinity? No, they're holomorphic everywhere except zero and infinity. Yes, of W in this case. So W, let us write 2n plus 1, dW for all n. And so it equals to 0. So but and now this integral is over the sum of C0 and C infinity. Let us expand T of W around 0. So let us compute this first integral. Integral around 0 or C0 T of try it of infinity.
Could you repeat why for the evidence novel and then argument tensor we think about the epsilon as being epsilon dw as the vector field? Why in the calculation we think just about the function?
Because so the first answer that because the meaning of epsilon was the coordinate dependent shift, because infinitesimal conformal transformation corresponds to z goes to z plus epsilon. So it is infinitesimal transformation, which is identified with a vector field. And it's easy to see because its action on functions is the following: z plus epsilon equals to f of z plus epsilon dzf plus. So the invariant object is epsilon dz. And in the Kac-Moody case, we had transformations like, for example, fermions psi alpha, psi star alpha, and go to psi star alpha plus epsilon. Actually, here we could write epsilon a. So well, it holds for any a. So here it was a transformation epsilon a of z, ta with well, ta alpha beta psi star beta. So it was a function. It was just some local rotation at each point z. Psi star alpha of z. Right. So if you transform psi psi as a one-half differential, this epsilon should not be transformed, and it is perfectly fine. And this expression is how to say it, covariant with the same weight. So it was the first answer. So isn't this answer clear? And the second answer is that the same can be done even in the cases when all these fields do not have such clear interpretation. For example, for some W algebras, or maybe for some supersymmetric algebras, no, maybe that case is better. Yeah. But in that case, the only requirement is that this object that we are going to integrate should be invariant. So we should multiply the W by something that has dimension 1. And if this current has dimension 1 already, we don't need to do anything. If it has dimension 1 minus 1, we should multiply it by something that is a component of some one form. Minus 2 some to differential. Or if it has dimension 3, then it should be multiplied by some object of dimension minus 2. So and in the case for double algebras that don't have a nice geometric interpretation. So, and the effect of this is that, for example, here the only field homomorphic in the entire plane is constant. But here we have three such fields, in a sense, dz, zdz, and z square, and z square dz. There are global homomorphic vector fields. And that gives some extra conditions. And for homogeneous surface, it is the opposite. Vector fields, homomorphic vector fields disappear, but we have instead some homomorphic differentials, one forms and two forms and so on. Is it fine? Okay, let's go to this. Well, maybe it's better to write this integral here. So it is v infinity. So what can I say about this integral? What does it equal to? Why minus? No, I'm just asking to use the OP of T of W with Y, because we are integrating around this precise point, around very small contour. So what will it give? So a reminder that T of W was Y of Z vector is sum, or a statement that action of the energy momentum tensor on the local fields, on the space of local fields, which is isomorphic to H, comes from, it is W minus Z to n plus 2. It comes from their local P. Mm-hmm. Yes. Mm-hmm. Yes. Uh, we have this, and can you say immediately what happens in the other limit, or is it better to write it explicitly? Mm-hmm. No, I would say again. What do you think? Yes, yes. L minus n. So, so go over C infinity 0 infinity. Uh, sorry, L minus n. Well, and also it is with the minus sign because when we go to infinity, we need to change the local coordinate, and this change of local coordinate gives us extra minus sign. So is it fine? So this defining relation for the space of conformal blocks now look like this. So there is some. Uh, so it says essentially that the Virasoro generators can be moved from 0 to infinity. And if we now identify this two-point correlator with some form on H uh, tensor H dagger, if we conjugate one of these two terms, uh, uh, well, essentially I want to say that we can identify the uh, infinity. We want to identify on this. Um, with this object. Or in other words, and this notation means ln agar equals to L minus n. So if we do this, if we introduce such a definition, and then what is written here? What kind of statement? Yes, and then there is this extra equality. So it means that the action on this vector can be moved and turned into the action on this vector, right? So uh, so let us call this formula 3 stars, or maybe star 2. Then star 2 is equivalent to this v infinity ln times v0 is equal to v infinity times ln v0. So, so in other words, we used some properties of this scalar product on the space of states of our theory, thinking by default that it is invariant under the conformal transformations. So this scalar product is this dot here. So we don't even think that it can be something between the states. But if you start thinking about the space of conformal blocks, it defines. So this definition defines explicitly that such kind of pairing on the space of states is invariant under the conformal transformations. And it means essentially that this dot commutes with the Virasoro generators. So before that, we simply omitted this dot. But for some cases, it is something important because, for example, this pairing can be between different states, and even even in this two-point case, the space of such pairings can have a higher dimension. But by the way, going back to original question about the dimension of such conformal blocks. Can you find it now looking at this relation? And also here we need to say that these representations H, C, delta are kind of factors of Raman modules. In a sense, L0, they have a highest vector on which L0 acts based on some number, and all other generators, all higher generators, all positive generators act by 0. So L0 on delta 0 equals to delta L. and greater than 0. So yes, yes. So suppose that we have some scalar product of this kind. The question is how many ways to define it do we have? Mm. Oh, first, if dimensions of if these vector spaces are two Virasoro representations with different highest weight, how many such scalar products can we have?
It will be just with zero.
Yes.
If you actually get zero on the left and on the right,
Yes.
you get absolutely zero.
Yes. So we have this from this argument. So the dimension equals to 0. And now if delta infinity is equal to delta 0. Mm-hmm. Yes. Uh, because we need to compute scalar products of this form. So here it will be some Ly prime. Here it will be L minus Y. Return delta. We can move this L generators on the left and on the right using the commutation relations. And finally, it equals to something, some number that depends only on the commutation relations times such scalar product. So the value of this bilinear form is proportional to so on any pair of vectors is proportional to its value on vacuum. So in this case, the dimension is equal to 1. And we actually I knew this in the sense that we knew that the space of we knew that two-point correlators can be fixed uniquely, and that they vanish when the two dimensions are different. So here we can write that it is delta 0, delta 0, delta infinity, or 1 or 0, depending on the dimensions. Mm. And I wanted to show you some examples that demonstrate that it is not automatic that such dimension should be 1, because we can consider so-called irregular representations, or don't know if it is the correct name, something like Gauss-Whittaker modules, or at least there is a term Gauss-Whittaker states. So So here we constructed something physical, something related to fields of dimension delta. But if you ask about abstract representations, we can consider, for example, this. We can take the first R universal generators. Let me think. LR. And ask them to act so I equals 1 to R. We ask Li to act maybe let's use big lambda by lambda I let me think. No, I equals to R to R to 2R. So like this. And if I this I is greater than 2R, and then they act by 0. So it is a well-defined procedure because why was I thinking about this range? Because Versal algebra has some non-trivial commutation relations, and they should be satisfied when we impose such conditions. So namely, Ln with Ln with Lm acting on the state should equal to n minus m L and plus m acting on the state. Or in other words, so Ln minus Lm lambda minus so if you ask this lambda to be the eigenstate of two Virasoro generators, okay, let me think if I wrote this correctly. Probably it should be fine. Yes, yes. So if you ask this lambda to be the eigenvector of two L's um, with positive numbers n and m, and they're different, then L with the index equal to some of these numbers should act by zero. So if we take, for example, L1 and L2 and ask them to act by zero, then L3 acts by zero immediately, and also all higher Ls. So if we ask this for the first positive Ls, and for example, if we ask L0 to act by some number, and so then L1 should act by no, this doesn't work this way. If you ask L0 and L1 to act by some number, then this the eigenvalue for L1 should be zero immediately. But it is only for positive n m. So n greater than zero. So if you take here 1 and 2, then here we will have 3. And this L3 should already act by 0. So to obtain some non-trivial representation, we should skip first R minus 1 generators and ask the state to be the eigenstate of LR. In this case, the first vanishing vector will correspond to R plus 1, because if it is R and R, it vanishes. And this will be to R plus 1. And so I have this range from R to 2R. So and let us look at this case. For example, at R equals to 1. Now, in this case, L1 and L2 act by some numbers. L1 on this state is lambda 1, lambda L2, and our scalar product is and this representation C lambda is spanned by vectors that contain also L0, because L0 acts in some non-trivial way. L minus n1, L minus n so some L0 to some power k. So, and we can consider two cases. One is when one representation is in the usual highest weight representation. And another representation is this relative vector module. And what is what is the dimension of the space? What do you think? Y3, what are the generators? What are the basis vectors in this space? In a sense, what are possible scalar products? So what should we do technically? We have one. We need to compute the scalar product of two vectors. One has this form as before. We have Ly prime acting on delta, and another state has this form. It is L minus Y at times L0 to the power k acts on lambda. Because before we can move positive L's to the right, they still commute with this scalar product. So we can move positive L's to the right, negative L's to the left. All positive L's act on this vector either by some numbers or by zero, but they disappear in any case. All negative L's act on this vector by zero. And what remains after all? Hmm? Uh, yes. So everything, so as before, everything reduces to the scalar product between delta and lambda, right? So dimension of the space is one, right?
Now I cannot take consideration about the delta of this lambda vector because it's not an
Yeah, yes, yes, precisely. So, so So you see, it is not. So in some sense, dimensional the space is bigger than the dimensional the space in kind of generalized sense, because this can be either 0 or 1, and it is almost always uh, zero. But in this case, it is always 1. And And now let us go further and try to consider the space of scalar products between h c lambda and h c lambda prime. Probably. So what? Maybe can I erase this? Mhm. Because I think the definition is super intuitive. So C lambda prime. What do you think? What happens now? Mm-hmm. Yes. So this lambda prime L so L 0 to power m L y prime L minus y L 0 to k lambda. It introduces to such a scalar product lambda prime of 0 to k plus m lambda, right? So so, so it is so dimension of the space is infinite. And now I want to show some typical example of how to deal with such spaces. So it is some abstract space, a space of all possible scalar products on this pair of Versor modules, irregular Versor modules, and we want to define some bases in the space. So one naive way to define the basis is to say that all these scalar products without zero are some, for example, ck plus m. If we fix all such numbers, then we have some scalar product. It is well defined, we can compute this. But there is more conceptual way. And since we can try to introduce some decomposition on the space of two-point functions, and namely, we can say that the following object is a scalar product. Let me. So, um, how to denote the scalar product? Let us say that there is this y of 0. Oh, too complicated. Let us simply use a dot with a subscript. V infinity dot with subscript delta v0 is by definition the following object. It is V infinity is sum over all y and y prime So we inserted the resolution of identity here using states in the module of dimension delta. So it is clear that we in infinity that this dot of this subscript delta commutes with else. Right, just by definition. Because else commute with the resolution of identity. So maybe it is some extra question which can be non-trivial, but in general people think so it should be proved. Generally, people think that such scalar products form a basis in the space of all scalar products. Mm. So. And this is the typical procedure. In a sense, this is precisely what happens for the usual endpoint conformal blocks. Are there any questions about this? Hmm? Uh, there should be some scalar products defined here. So let me think how to do this. Hmm? Yes, but it is so the situation here is kind of similar to the Fourier transform. In a sense, if you have functions on a circle, then naively it is uncountable versus countable, but the spaces are the spaces have some scalar products, and so they are just Hilbert spaces which are all isomorphic. So situation here is the same, but I don't know at the moment how to define define scalar product on such conformal blocks. But in a general situation, when people define a scalar product on conformal blocks, it is something like the integral of absolute value of this function of z squared times some measure which is also constructed, I think, from some different conformal blocks, and this is integrated over over the whole modular space. So I cannot write the precise definition, but the point is that if we think about basis, completeness, and so on, we need to define some scalar products, and it is some trivial problem. So I think there should be some papers by Teschner or very recent ones by Eberhard about some properties of space conformal blocks, and probably some definitions can be found there. But usually when people think about such such objects, they think about them as about such decompositions. And in the case when we can define such a decomposition, but for example, it can be even worse, because here we took just first two L's and asked them to act by numbers. So this space had a dimension 1. But if we take more L's, if we consider R equals 2, then even this space will become infinite dimensional, and we will suffer. In a sense, it becomes a highly trivial problem to define some decomposition of the space, some reasonable representation. And the answer to the question why it happens is that such states can appear can appear as limits of normal endpoint conformal blocks. For example, this state can be obtained from the highest vector acted by the vertex operator. They have two dimensions and the distance, and when we send this distance to 0 and dimensions to infinity, we get such a state with two parameters. And also, this state can be represented as some vector in such a Verma model. So this essentially suggests such a representation that we can say that it is not just some abstract module. It is some module that contains infinite linear combinations of vectors of this module. So we can simplify such a vector here. The vector satisfying these two conditions. So, have any questions about this? Okay, so let's go further. Maybe. So what can I erase? Maybe let us erase this board. This was earlier. What about this dimension? Mm, mm, delta infinity, delta 1, and delta 0. Hmm? Yes. And hmm? Hmm? So I'm going to say it again. Yes, but there should be some extra computation to the one we already did. Because so mm, what did we compute on the last time? We computed such matrix elements where there was y of infinity L minus y prime delta infinity mm, y of mm, y of 1 delta 1 y of mm, 0 L y of minus y delta 0. So we were computing such matrix elements, and we found that they can be expressed they can be expressed in terms of of uh, uh, the correlator with only the highest vectors. But let us actually try to think about this a little bit more. So, so in a sense, how to compute this? So we want some relation that moves Virasora generators from here to here. And this relation is again, so we have delta infinity acted by Ly. We have y of mm, y of 1 delta 1 and we have some L no minus y, So it is Ly prime y on delta 0. So we want to move this generators to the left and to the right. And to do this, we need commutation relations between Ln and y1 delta 1. And the question is, what is this commutation relation? Without anything. Without anything. No, because what is this? It is the contour integral of dz z to the n plus 1 t of z y of 1 delta 1. Yes, so it is the integral dz z to n plus 1. So it is 1 over z minus 1 squared y of 1 L0 yes, delta 1 plus 1 over z minus 1 y of 1, and here it is just L minus 1 delta 1. So in principle, we know that if we make this one z dependent, then it can be written as z derivative. But abstractly, it is just L minus 1 acting on the state. So the fact that it can be computed can be obtained without using any analytic computations using some explicit z dependence of these functions. It can be done simply algebraically. Yes, so if you compute this integral, we get just y of 1 so n plus 1 y of 1 L0 delta 1 plus y of 1 L minus 1 delta 1, right?
Sorry, but before we got the OP between t of z and y, we had the sum to sum over all possible n.
Yes, but if you take positive elements, they will contribute to higher order poles, but they act by zero. They act by zero on this highest vector. And so the only and if you take negative L's less than minus 1, then they will give regular terms of this expansion. So half of them vanish for one reason, half of them can be neglected for another reason. So is it okay? Mm-hmm. So if we do all this, so we see that each time we do this, we obtain some L0s that act by numbers and L minus 1s that, well, in principle, we can insert here some dependence and write the derivative. But let us keep it as is for a while. So this equals to something And finally, it is some combination of such matrix elements. Y of 1, L minus 1 minus 1 to the k delta 0. So this is what happens if we just use definitions of the OP and the Russell algebra relations. The question is how to compute such matrix elements. The answer is the following. We can do the same for L0. So in particular, here we have that L0 commutator with y of 1 delta 1 is so here it's just L0, y of 1 0 on delta 1 plus y of 1 minus 1 delta 1. Sorry, it is delta 1. So this way we can so we can use this relation with O0 to do the same for we can use this relation with O0 and insert it into the arbitrary commutation relations, writing here something like this. So it will be n plus 1 y of 1 O0 acting on delta 1 plus such commutation relation L0 with y1 delta 1 minus delta 1. So it is a structure. This O0 will act on delta infinity. This then we will have L0 acting on delta 0 with minus sign, and there will be a delta 1 acting on delta 1. So in total, it produces the term like delta infinity minus delta 0 minus delta 1, which will produce something like this, plus n. Because I'm using this relation and substitute it here. So I take this and put from this term. So L0. So delta 1 is the eigenvector of L0.
So then after the zero.
Hmm? Oh, yes, yes, thank you.
But then I could do it also with the first piece.
Uh, yes, of course, yes. Yes, I could simplify this and delta 1. And we can cancel this one. So so in our computation the last time this um, action of L minus 1 produced some derivatives of z to some powers, and in this algebraic computation these derivatives correspond to these three actions of L0 on delta 1 on the left and on the right. So these three terms. Two terms here and one term here. So if we can cancel this one with this one. So such computations are possible because our field has dimension 2 and we have a little bit more homomorphic vector fields, so we can express this L minus 1s to k to as as the action of L0. So this finally transforms to something times delta infinity delta 1 delta 0. So it is one part of the story. Another part is that we computed such matrix elements only for the highest vector here. And but in principle, we need to know this conformal blocks for arbitrary states. Maybe it's, well, probably it should be enough. And to get them for arbitrary states, we can do the following. So let us simply write by definition that y of 1 L L minus k on some vector equal to the integral dz over 2 pi I z minus 1 to k plus 1. All right. No, probably minus k plus 1. Yeah, like this. T of z, y of 1, L minus k, 1 v. And then it can be written as the sum of two integrals. So this is an integral around 1, and we can rewrite it as the integral around infinity, or around absolute value of z greater than 1. So here it's radially ordered. Minus plus the integral over z less than absolute value of z less than 1. of z. So this produces negative modes of t. Sorry, I forgot this factor. Z minus 1 to minus k plus 1. And here again, z minus 1 minus k plus 1. Well, this produces negative modes of t. And here it will produce some positive modes, some ln's. And these integrals produce such modes. Because we here we expand z minus 1 in positive powers of z, right? Let me think. No, there will be some mixture of positive and negative modes, but in any case, we see that the action on the state at point 1 can be moved to the action on the states at points 0 and infinity, right? So we had originally some contour here, and we can move this contour to some of contours here and here using this defining relation for the space of conformal blocks. So it's kind of the first step. We choose this point 1 and remove all Virasoro generators from it to 0 and infinity. And once we do this, we perform this computation with the highest vector at 1. Is this clear? So, and yes. So it's actually 1, and this way we can compute such trilinear form at any states in the Virasoro modules. And by the way, if you look at this example, we see that the space becomes infinite dimensional because here we had this L0, which could act only on one of these states, and will be unable to move this L0 through the vertex separator, because to move it, because we had another problem. We had L minus 1 that had to be expressed in terms of action of L0s. And if we don't know the action of one of these L0s on the right, then we cannot express the action of L minus 1 in terms of numbers. So we already run into this problem. And to resolve it, we'll need again to insert some resolution of identity, or to have some control of these conformal blocks. Okay, and so now the general strategy to define the space of conformal, to define some vectors in the space of conformal blocks is the following. We should take our Riemann sphere or well, basically Riemann sphere with punctures, and cut it into some pieces such that spaces of conformal blocks on these pieces are one-dimensional. So if you have, for example, if you have the four-punctured sphere, uh, uh, so uh, dimension of this space is infinite. But we can say that conformal blocks on the sphere, no, let us call it conformal blocks. They can be represented as a direct sum over all intermediate deltas of conformal blocks on such spheres. Here is delta tensor. And this corresponds to such conformal blocks correspond to insertions of resolution of identity, in the sense that if the two functionals satisfy this defining relation, and we introduce and we glue them using this resolution of identity, then the resulting object will also satisfy the same relation, because a length commute with the resolution of identity. This contour encircling all singularities shrinks to zero on both parts of our three-punctured sphere, and it is the same as here. So this can be drawn pictorially, like we have some bold points that correspond to irregular states, some lambda primes. Conformal blocks of this kind are isomorphic to a direct sum over delta of conformal blocks on such sphere. Delta tensor conformal blocks on such sphere. So, and this spaces are one-dimensional. So this is the basis in space of these conformal blocks. So, and if they are conformal blocks, and what we computed last time was such such a vector in this space corresponding to mm, was a vector of the space corresponding to dimension delta computed at the highest vectors. And if it is torus, so basically, if we work with spheres or with Riemann surfaces with punctures, they should be cut into this into such objects. For example, if it is a torus with one puncture, then it should be equal to direct sum over deltas of conformal blocks on a sphere with delta and delta on both boundaries. And so on. So in terms to get one-dimensional subspaces in the spaces of conformal blocks, we need to fix intermediate dimensions. So, and also, you can notice that this decomposition is not unique. We can cut it, for example, in different ways. So it is also isomorphic to some of conformal blocks of this. Tensor conformal blocks with some delta prime. And since we have this equality, we have some crossing invariance of conformal blocks. That conformal block in the S channel of delta t equals to a conformal block in the T channel of delta prime t integral over delta prime with some fusion kernel. So it is on this equality. So I'm saying that. Hmm? Well, I denote. Well, let me use just this picture. So I was using S channel and T channel. So it equals to a conformal block with different decomposition. Well, let me write let me write it like this. So this corresponds to this decomposition. This corresponds to this decomposition. A conformal block in the sense well, it's a conformal block is functional in this vector spaces, but if we computed but everything is proportional, everything is expressed in terms of conformal blocks computed for the highest vectors. And then if you know how to transform conformal blocks on the basis vectors, then we know everything. And there is such a relation which can be understood either as a relation between conformal blocks as functionals defined in this way, or just their values on the highest vectors.
So B is the value of an for highest vector.
Yes.
This is the element of the tensor product of
Yes.
B
Yes. And as so, we can maybe indicate this explicitly that this conformal block is a function of t. This is when t goes to 0 and 1 is goes to infinity, and this conformal block will be a function of 1 minus t. So there are such kind of relations. Mm. And for example, some of these conformal blocks equal to delta hypergeometric functions, and this equality is precisely the and the how is it called? Well, a correction formula for the hypergeometric functions. And actually, uh, all the special functions which appear in CFT, or almost all of them, come from the corresponding matrices for the hypergeometric functions. So there are some gamma functions in that case, and all CFT, well, almost all CFT special functions come from some difference relations with these gamma functions. So, uh, so all this is based on the global properties of hypergeometry. Yes. Yeah. So yeah. In the general case, it is some complicated function. So for example, if it is an arbitrary central charge, it is given by some integral with a lot of double gamma functions inside. But if it is c equals 1, there is an explicit expression as some product of bounds G functions, like double gamma function with the same periods. And also, and if we go to C equals infinity case, it is also known, and it is a bit similar to C equals 1. In that case, it is a generating function for canonical transformation between different Mondrian manifolds. So, okay, maybe that's all. Do you have any questions? Well, next time I plan to talk about the cases when on this when the space of conformal blocks and becomes a finite dimensional for Irregular and for the KZ case, well, BPZ and KZ equations. Hmm? Mhm. Yes, of course. In a sense, this so yeah, I should have said something. Mm, so it's not just space of conformal blocks on this. Uh, mm, how to how shall we call this? Ah, no, is
We should multiply for the cylinder from that to that.
no, but as the vector space, it is the same because it is something one-dimensional. We simply need to say how to compute such such mm, functionals. Namely, we need to take this vertex operator and take its trace with Q to LZR. So, hmm? uh, so how shall we cut this? Mm. So this can be cut. So there are three intermediate dimensions here, here, and here. Or it can be cut also in some other way, for example, like this. And actually, it is the case for the torus as well, because this torus can be cut this way, uh, but it can also be cut this way, which corresponds, so in this picture, it corresponds to cutting along the A cycle and along the B cycle. So one expansion is in powers of so where to write this? So one expansion is in powers of q equals to e to the 2 pi I tau. Another expansion is q check, which is e to minus 2 pi I over tau. So it is the modular transformation. Yes, yes. Uh, conformal blocks of Q-check will be given by some linear combination of conformal blocks of Q. And here the situation is very similar to this 4-point conformal blocks. In a sense, there is even some relation between toric conformal blocks and 4-point ones. They can be expressed in terms of each other. And here also, this connection constant is known explicitly for C equals 1. So we still have to write a paper about this, but it will be soon. And for C equals infinity, it is also something simpler. Mm. And if you put here a trivial vertex operator, then this crossing symmetry gives modularity of the characters of some representations. Oh, no, not necessarily modularity, in the sense they can be permuted, but usually this modular transformation acts as some finite representation. Okay, so any other questions?
What do you take? What do you get if you cut in the other circle?
On the torus,
Yes.
we'll get conformal blocks of different.
What shape?
It is still a torus, because, well, maybe it is not so obvious here, uh, but it should be obvious in this picture. So we have A cycle and B cycle. So it is one. It is this is tau. So we see that it is a more or less equivalent. So one way we get such a long cylinder with a hole, and in the other direction we have a very thick cylinder. So it can be drawn like this. So one cylinder is this. Another cylinder is this. Oh no. Maybe it's no, it's it's not very precise picture, but so I'm imagining that it is already glued in that direction. Or maybe let me remove this identification. Then it will look like a normal picture of a cylinder. So originally it should be a torus, and it should be identified. And if you cut it, we get something like this. Mm. Mm. Or maybe it should be clear, more or less. Mm-hmm. Oh, yes, of course. So we have one form in the stores which is dizzy. It is holomorphic, and it has two periods, 1 and tau. So so info. And yes. And for homogeneous surfaces, each such cut will give one complex number. In a sense, it gives us the prescription of how to identify this spaces of boundary functions. So It defines a mapping between one region of this functional sphere and another region. So, and on the CFT side, it is an insertion of some Q to power of 0. So, so we can say that mm, uh, any such resolution of identity also comes with a Q to L0. And put it here. Q1 to L0, Q2 to L0, Q3 to L0. So such conformal block will depend on three complex moduli, which is consistent with the formula 3G minus 3. Yes, yeah, so dim MGN for G greater than 1 is 3G minus 3 plus N. And this can be computed from this Pans decomposition. So N and N is just a number of positions of points. Okay. Do you have other questions? Okay, then thanks for your attention. See you on Thursday.